The foundational tools of modern analysis, specifically the infinite power series for sine, cosine, and arctangent, are almost universally taught as European discoveries. Open a standard textbook, and you will find these equations credited to Isaac Newton and Gottfried Leibniz in the late 17th century. But the actual derivation of these equations predates the European calculus by roughly 250 years. They were formulated in a strip of land covering less than 1,000 square kilometers in southern India. This region was home to the Kerala School of Mathematics and Astronomy. From the 14th to the 16th centuries, the scholars in this network developed the early framework of calculus. Mathematical leaps of this magnitude do not occur in a vacuum. The popular image of a solitary genius discovering fundamental truths in isolation is misleading. Deriving an infinite series requires a systemic, multi-generational infrastructure to support the continuous refinement of ideas. In medieval Kerala, this infrastructure was built by two distinct forces. First, an agrarian economy that demanded precise seasonal calendars, and second, an inheritance law that granted scholars unlimited time. This early invention of calculus was the result of an arrangement of land wealth and domestic laws that provided the human capital necessary for centuries of research. To understand how the Kerala school broke through to the infinite, we have to look at the mathematical constraints they inherited. The baseline for classical Indian mathematics was established in the 5th century by Aryabhatta. This diagram illustrates Aryabhatta's method for approximating pi. He used finite geometry, calculating the perimeter of a regular polygon inscribed within a circle. By scaling that polygon up to 256 sides, he established a strict algorithm. Add 4 to 100, multiply by 8, and add 62,000. Divide that result by 20,000, and the output is 3.1416. While the math was highly accurate, it was bound by the aphoristic tradition. Complex algorithms were compressed into cryptic, poetic verses. This was a necessity for rote memorization in a culture that transmitted knowledge orally. This medium forced early mathematicians to provide the operational rules without accompanying logical rationales or written proofs. When they did record their work, it was on palm leaf manuscripts. Space was physically limited, leaving no room to record the step-by-step derivation of a theorem. Pushing beyond these finite approximations to work with infinite series required a shift in how knowledge was recorded. The scholars needed a way to process massive datasets and share their derivations across generations. Classical Indian mathematics was a formidable system, but it had reached a structural ceiling, bounded by finite geometric models and a proofless poetic medium. Breaking that ceiling required a completely different social environment. That environment materialized in medieval Kerala. The architects of this mathematical tradition were a group known as the Namboothiri Brahmins. As they settled into the region, the Nambuthiris established the Janmi system of landholding. This structure concentrated vast agricultural wealth and property directly into their caste, establishing them as the apex economic power. To keep this wealth concentrated, the Nambuthiris enforced a specific system of patrilineal descent. Under their form of primogeniture, only the eldest son was allowed to inherit the family property and marry within the caste. The younger sons faced a different reality. Explicitly barred from managing property, they had no traditional family obligations to maintain the estate. This inheritance loophole created a massive subclass of highly educated men who possessed absolute leisure time. Their material needs were provided for by the estate, leaving their days entirely unencumbered. These younger sons lived and worked in traditional homes known as illums. Within these walls, shielded from physical labor and economic anxiety, they dedicated their lives to intense intellectual pursuits, ranging from philosophy to mathematics. These inheritance laws inadvertently supplied the most critical resource for scientific discovery, a constant supply of highly educated, unencumbered human capital. The scholars focused their attention on the calendrical forecasting required by the temple-centric agrarian economy. Accurate harvesting required tracking the exact positions of the moon, the sun, and the planets. To optimize yields, these scholars had to measure celestial anomalies to extreme fractions of a degree. This required processing and storing data at a scale previously unknown in the region. To manage this information, they utilized the Katapadiye system. This was an alphanumeric cipher that allowed them to encode massive datasets and specific fractional values into syllables that could be easily memorized and passed on. The combination of agrarian data demands and a permanent labor class birthed the Gurukula system. These were master-disciple networks where specialized knowledge was relentlessly refined and shared over generations. This map traces a multi-generational research program from 14th century Madhava to Paramesvara, Nilakantha, and Jashtadeva. Nilakantha's breakthrough placed Mercury and Venus in eccentric orbits around a mean sun orbiting the Earth, accounting for the equation of the center, predating European models. Limitless time, structured transmission, and strict agrarian data demands pushed this network to test and iterate their models against physical reality. That continuous feedback loop allowed them to break past the limits of finite math. The culmination of the Kerala school's centuries of research arrived in the 16th century with a text called the Yukti-Bhasa, written by Justadeva. This work abandoned the use of cryptic, memorized verses in favor of the concept of upapati, or rationale. Justadeva used step-by-step written logical proofs to verify his theorems. Written in the regional Malayalam language rather than formal Sanskrit, the Yukti-Bhasa provided the explicit derivations for Madhava's infinite series. By laying out the rationale for evaluating sums and interpolating trigonometric tables, it functioned as the first textbook of calculus. This timeline graphic compares the European sequence of mathematical discovery against the Indian sequence. You can see the Kerala school's output comes to an abrupt halt. The invasion of the Mysore sultans and the subsequent establishment of British suzerainty dismantled the socio-political structure of the region. The Janmi system fractured, the temple economy lost its autonomy, and the support for the Ilms vanished. The standard map of mathematical history shows a single line running from ancient Greece to 17th century Europe. That map is factually incomplete without the chronological data from southern India. Reaching into the infinite is the result of a socio-economic architecture that grants generations of scholars the time to look at the stars and calculate exactly how they move.